what as quick definitions, waveguide quantum electrodynamics, we could say, studies the interaction of light and matter at the quantum level. And this can be done using both natural and artificial atoms that are coupled to a 1D electromagnetic environment, which is the waveguide. And since it was Dibindu who invited me, I'll just mention that, I mean, it's almost 4 years ago now, we published a review paper together on the very early days of this field, but it's only continued to grow since that time. Okay. So since I think this is a fairly varied audience, let me give some very basic introduction or a quick introduction to the systems that we're working with. So as I said, waveguide QED now can be done in both natural and artificial atoms, and then with natural atoms coupled to optical photons, typically now in dielectric waveguides. And then it can be done with artificial atoms, which are superconducting qubits. Can we mute ourselves?
Yes, I have muted the person.
Sorry. So this can be done in our systems. We're doing this with artificial atoms in the form of superconducting qubits. And they're coupled to microwave photons, because these are the typical frequencies that we make our superconducting qubits that are confined in on-chip superconducting waveguides, with coplanar waveguide being the particular geometry that's most common. And here's a micrograph of one of our typical systems. So the waveguide is what we see here. So we have just a strip of a superconducting metal, often aluminum or sometimes niobium. And then it just has a gap between that and two ground planes. So the dark is just silicon substrate underneath, and the light is the aluminum. And so this waveguide can tightly confine superconductor or microwave photons. And then what we see here, which I'll talk about a little bit more, is the qubit. So in the center, what we actually see are just two capacitor plates. And then what you can't really see in the middle here is a superconducting Josephson junction that completes the qubit. And then, as my little animation was maybe meant to suggest, the idea is we can have photons kind of zoom in and out of this system interacting with the qubit. So how do we make an artificial atom or a superconducting qubit? So we could think of basically, well, we could start with some electrical circuit and try to quantize it. The simplest one of the simplest and most common electrical circuits we could think of would be just a harmonic oscillator, so an LC oscillator, so made from an inductor and a capacitor. Now the problem is that a harmonic oscillator doesn't work as a qubit, and that's exactly because it is harmonic. So if I think of having a quantum description of a harmonic oscillator, the frequency for transitions from 0 to 1 is the same as from 1 to 2 photons or 2 to 3 photons in the oscillator. And that means I can't do quantum control on the system. So if I apply a tone to drive the 0-1 transition, once I have some population in the 1 state, I'll start to drive to the 2 and to the 3, and I essentially just get diffusion through the state space. So to make it addressable or controllable, or to make it a qubit, we need to make the system nonlinear. And so the way that we do that is essentially to replace, in superconducting systems, is to replace the linear inductor by a nonlinear inductor, which in detail is a Josephson junction, which I'll also introduce. But when I do that, now I get a new spectrum, which if I can make the nonlinearity strong enough, I can make this oscillator nonlinear at the single photon level. So now the frequency or energy of the 0-1 transition is distinct from the 1 to 2 transition. And now I can do quantum control, or I can say drive Rabi oscillations on the 0-1 transition without leaking out of that subspace. And so, there are a number of different types of superconducting qubits, but the one that I've described here is commonly called the transmon qubit, and it's really the most common. So Google, IBM, Rigetti, the big quantum computing companies all use this transmon style qubit. which you can really think of as just a very nonlinear oscillator. Okay. So again, as just as some introduction, so what is, I mentioned that this key element that makes the system nonlinear is this nonlinear inductance or Josephson junction. So here's a little cartoon of a Josephson junction. So if you don't know what it is it's just a tunnel junction between two superconductors. So I imagine I have two pieces of superconducting metal, and I have a very thin insulating barrier, which is typically, in real devices, a couple atoms thick. And then you can have essentially the superconducting wave function and the two sides, leaks across, and there's some overlap. And so I can get some supercurrent through this device, even though there's an insulator. And this is the Josephson effect. Now, I won't go into too much detail, but from our point of view, we can write down what are called the Josephson relations, which essentially define the IV curve or the dynamics of this device in current and voltage. And they look like this. So I say I have the current is the sine of some variable phi. And then phi I can define as the time integral of the voltage. So this, in terms of a circuit equation, this looks a little bit funny, but if I think about how I can actually write the equation or constitutive relationship for a regular inductor, often you see it written as a differential, like, the voltage is the time derivative of the current, but I can also write it in this integral form, right? And so then we see that, for a linear inductor, we have that the current is just a function of this time integrated voltage, right? So now it doesn't look quite as strange. And then I see that the Josephson junction now, in this sense, just looks like a nonlinear inductor, right? So now I have a nonlinear function of the voltage, but I can obviously now expand this sign to first order, and I recover just a linear Josephson junction. And then, of course, if I go to higher order, I get a nonlinear Josephson junction. And I won't emphasize it here, but for any circuit, I can define this phase variable, which is the time integral of the voltage. But as it turns out, in a superconducting system, we can actually formally associate this with the phase of the superconducting condensate, or the phase of the superconducting wave function, which is important, but again, I won't emphasize it here. Here's just an SEM, scanning electron micrograph image of a real Josephson junction. So this is a typical size Josephson junction we would have in a transmon qubit. And what you see here is we have one aluminum electrode, we have a second aluminum electrode, and then in the overlap of the electrodes is this thin insulating barrier. So what we do in practice is we deposit this layer, we just let in some oxygen into the system, so the aluminum oxidizes, forms aluminum oxide, and then we deposit a second electrode on top of it. And the scale of this is, for a transmon, of the junction is a couple hundred nanometers. Another related but important device to introduce is the SQUID, or superconducting quantum interference device. And this is basically two Josephson junctions put in parallel in a loop. And squids are used for many different things, but the main thing here is that when I make this squid device, I essentially make, or effectively, a tunable Josephson junction, or a tunable inductor. So by changing the magnetic field through this loop, I change the inductance of this squid. Or again, I can think of it like a Josephson junction where I can tune the effective energy of the Josephson effect. And this is very useful in superconducting qubits because it allows me to make tunable qubits, which we'll see a number of times. So I can make a device in situ. I mean, I can make a qubit, and then by using an external magnetic field, I can tune it in situ, which gives us a lot of flexibility in experiments. Okay. So now that we have a little bit of a sense of what our artificial atoms are, let me get back to talking a little bit more specifically about waveguide QED. So as I mentioned, I would say waveguide QED is really the study of light matter interaction. and it happens to be in 1D. But what's really been kind of, I think, impressive over the last decade or so in this field is how we've been really able to study new regimes of light matter interaction in these systems. And so if we think, if we think of our description of light matter interaction, or the interaction of photons and atoms, traditionally there are really three key approximations that are made in treating this interaction. So first is a dipole approximation, which is essentially an approximation that the size of the atom is small compared to the wavelength. The next approximation is a Markovian approximation. So we kind of assume the coupling is weak, and then the bath that we're interacting with for the atom, which would be the electromagnetic field, essentially is featureless or has no memory effects. And then the final one is the coupling is treated as perturbative in general. So even in the so-called strong coupling regime of circuit QED or cavity QED, the coupling is actually still very much perturbative. So there are these key approximations, and the kind of remarkable thing is in the last decade, we've been able to, or the field, not we, myself, has been able to break all of these approximations and study these new regimes. So for instance, we and others were able to experiment in what we call the ultrastrong coupling regime, where we had, again, a superconducting qubit, in this case, a different type of flux qubit coupled to a transmission line. And we were able to design this such that the coupling rate of the qubit to the line was actually larger than the qubit frequency. And so in this case, clearly we break the non-perturbative. The coupling is a larger energy, so it's obviously not perturbative. And then this tends to kind of naturally break the Markovian approximation, just because the spectral density of the bath or quantum fluctuations isn't flat or white. Although in this case, we still had the dipole approximation holding. This qubit is much smaller than the wavelength. Another thing that we've been able to do, again, us and others, is to study self-interference effects. So we had an old experiment where essentially put a qubit or an artificial atom in front of a mirror. So, at the quantum level, the atom interacts with, it can kind of emit a photon. That photon can bounce off the mirror and re-interact with the atom. But this can also all happen virtually. And these effects have also been studied in related systems, so qubits coupled to surface acoustic waves. And you can see now all kinds of new and interesting effects. And so in this case, so for our experiment with superconducting qubit, with microwave photons, the dipole approximation would still hold. In other experiments by people with surface acoustic waves, they break the dipole approximation. All of these self-interference effects very much break the Markovian approximation, because now we have memory. This is the bath remembers you emitted a photon and then it's come back. And that changes things quite a bit. Although, then these experiments have been done with perturbative coupling. Something that's happened even more recently is making physically large atoms. So this was first done, so I think work started at Chalmers University and Per Delsing's group, where they took the same superconducting qubits that I just mentioned, but now coupled them, essentially fabricate them on a piezoelectric substrate. And then these qubits can emit a type of phonon, which is called a surface acoustic wave. So we essentially just have ripples in the surface of the substrate that, because it's piezoelectric, the mechanical deformation also creates an electrical field. And so these mechanical waves can then couple to the superconducting qubits. And then because the speed of sound in the material is so much slower than the speed of light, the wavelength of these surface acoustic waves is very short. So in these systems, using a typical size transmon, they're now interacting with waves that are much smaller than that. So these can reach kind of a ratio of the size of the qubit to the wavelength of between 1 and 100. So obviously, very far outside of the dipole approximation. And again, you get interesting, essentially really like self-interference effects here, because now, the two sides of your artificial atom can actually essentially emit independently, and then that emission can interfere with itself. So really the qubit can interfere with itself in its own emission. And it was really just I know the people in this group, I mean, they were really forced to come up with this theory, right? So they were trying to understand, how can we treat, this kind of quantum coupling between the superconducting qubits and these surface acoustic waves. And one of the things they realized very early on is that, they break the dipole approximation. So they had to reformulate a lot of things of cavity QED in terms of, these big atoms. And so this again, here we break, in these systems, we break the dipole approximation and the Markovian approximation. So, this is a big point. These three key approximations, which kind of stood for 40, 50, 60 years, have been broken, at least, maybe not all in one experiment yet, but they've all been broken, and different effects have been studied in these systems.
Hello, I have a question.
Yeah, please go ahead.
So would you be able to take questions during the seminar or towards the end?
Yeah, sure. No, I'm fine if people have questions.
Okay, so there is already one question in the chat box. So this is from Arush Murali. The question is, would the surface acoustic waves and phonons also generate electricity due to the piezoelectric substrate?
Yeah, so that's exactly, so that's how you get a coupling. You could still think of the transon mainly being an electrical device. So it's still an electrical LC oscillator in this case, but then it's coupling to these mechanical waves. And the coupling is happening exactly through the piezoelectricity, right? So the way, when they want to generate surface acoustic waves to say bounce phonons off of the qubit, they do that. They have an interdigitated capacitor, so just metallic fingers, that are spaced kind of wavelengthy size. And then they just drive those at a certain frequency. So you put it in an electrical drive, and that generates the mechanical waves. But then those mechanical waves that are propagating are generating an electric field. And so when they pass under the qubits, they talk to the qubit through the electric field that they generate. So essentially the piezoelectricity of the substrate itself makes an automatic transduction between the mechanical and the electrical waves here.
So he has another question. I can request him to unmute himself and ask the question.
Yeah. Sure.
Why are transmon qubits more commonly used? Are they easier to create and maintain?
Yeah, so I think exactly. I think just over the years, they've been found to, I think they're just very reproducible typically and easy to use overall. Now to get to multiple nines of reproducibility, that's still hard, but, I think basically, you can go and make a transmon qubit and it will just work. And there are some technical details. The predecessor of them, charged qubits, were very susceptible to charge noise in the environment. Transmons were designed to be less susceptible. And you have things like flux qubits, which are still used in some cases, especially now for quantum annealing. But they have very tiny junctions, and the qubit parameters there are exponentially dependent on some of the fabrication parameters. And so that means that, they're kind of very hard to kind of fabricate, with good parameters on a large scale. If I want to make one and I can just make a few devices and I pick the one that works, that's fine. But if I want to make thousands or tens of thousands, exponential sensitivity is a problem. Okay.
Yes.
Okay.
Yes.
Okay. So what this first section of my talk, I'll focus on this kind of breaking of the dipole approximation, which is some of our more recent work. And so I'll just emphasize that. So I'll just to give some parameters. So again, what does the dipole approximation mean? The idea is that I have an atom which is very small, and in particular, it's much smaller than the wavelength that it's going to emit. So I can define kind of the critical ratio, which is the size of the atom to the wavelength, and this is typically much less than 1. So if we look at kind of traditional circuit or cavity QED systems, so when I had atoms in an optical cavity, this parameter is something like 10 to the minus 4. When I had Rydberg atoms in microwave cavities, it's 10 to the minus 6, 10 to the minus 4, so deeply, perturbative in terms of the size. And then, microwave or qubits in traditional systems kind of get to bigger numbers, but still even 10 to the minus 1, even if it's orders of magnitude bigger, it's still perturbative, right? So I just described how I talked a little bit about how saws could change that. And so, yeah, what's the idea of a giant, going from the dipole or small atom regime to a giant atom? The point is now I have an atom which is much bigger than a wavelength. And so it can couple essentially kind of in many places, or you could imagine it emitting and having self-interference. So again, with the saws, because they have a very small wavelength, these numbers can be very large. And you're very strongly in this regime. But we kind of asked the question, or really Anton Frist-Kokum at Chalmers, who did some of the saw work, he also had a clever idea how we might be able to do this in the microwave regime. So for our transmon qubits, they're typically hundreds of microns in size. And the wavelengths of microwaves that we're using is kind of centimeter. So they're still in this kind of small atom regime. But Anton had a clever idea about how we might be able to make an effective giant artificial atom in a waveguide QED system. So the idea here was that, okay, even though we have an atom that's much smaller than the wavelength, because we can tightly confine our photons in a waveguide and route them, move them around on chip, what we can do is we can take a waveguide, so that's routing our photon, we can bring it close to our atom so it interacts, and then we can let it go away and kind of meander around on the chip, kind of a wavelength scale distance, and then we bring it back to the atom and have it interact again, and then we can kind of repeat this, right, for a certain number of connections. So our atom is now still, the real atom or the real artificial atom is physically small compared to the wavelength, but it interacts at many different points. So it effectively it becomes a giant atom as far as the photon is concerned. And so, yeah, so Anton made predictions about this. And so, a first thing that you get is that I can get now a very strong frequency dependence of the coupling between the atom and the qubit, which is really it's an interference effect. And again, you could think about this, I'll kind of make this point a few times during the talk. I could think about, this is a perfectly classical interference effect, right? So if I had something emitting real photons or real classical waves, I get this interference. But an important point is that this really happens also at the level of level of amplitudes. So this is really quantum interference. And the point is, and why is it important to call it that? Because things that I'll state here also applies to the qubit's interaction with vacuum photons or with the electromagnetic vacuum, which controls the coherence properties. And you can think about that as kind of interference of virtual photons, or not. But the point is that it applies, everything we talk about, this classical interference applies equally well, thinking about the quantum vacuum and any kind of virtual transitions and things like that. So that's an important point.
Hi, Chris, can you hear me?
Sure.
Yeah.
Yes.
So at each point, like x1, x2, and x3, when the Hamiltonian you will consider, are they within dipole approximation? Like each point, x1, x2, and x3, the two-level system coupling with the photon?
Yes, I think so. Yeah, so the interaction here, the individual interaction in this case is small, and then you just have kind of these multiple of these small interactions kind of spread out.
So when you say that dipole approximation breaks down, you mean overall the effective coupling?
Yes, exactly. So for this system, so I mean, you see these effects. So for instance, I write this as a coupling, like this gamma 1, 0. So this notation means like the relaxation rate from 1 to 0, which is also then the coupling of the system to the line, or the coupling of the system to the bath, so the electromagnetic vacuum. And so you can see, this is the calculation, but I now effectively get a bath, which is very much not white, right? So it's in this sense, this is one of the senses, which is we can say, we break the dipole approximation. So we create an effective bath for the system, which is very much frequency dependent, or very strongly frequency dependent, which is what you would naturally see for an atom which is giant, right? Okay. So it is, it's not exactly the same as the surface acoustic waves, but it's kind of, you can get much of the same flavor. Yeah, so this is a theoretical plot. I mean, it's not so surprising. When I have these multiple points, I have interference, and I can get this very sharp, sharply frequency dependent interaction, where I can have, at some points, I have constructive interference. So say when the spacing is wavelength, but I can also have points where I get destructive interference. And also, not so surprising, the sharpness of this frequency dependence depends on the number of connections that I have. So for instance, here we draw the dark blue is for 3 connection points and the light blue is for 6 connection points. And roughly it's twice as sharp when I have twice as many connection points. And just to say, I'm scaling this, the frequency here, which we'll do in many plots, is scaled to what we're calling a mega lambda. And this is just the frequency essentially corresponding to the separation between the connection points in the system. Okay. So another interesting point, so this is kind of the first thing we can say when we make this system, is that we're going to get this frequency dependent coupling, which can be useful by itself. It can be kind of a way of hiding the qubit from kind of vacuum fluctuations or decoherence in the line. So if I can move between strongly coupled point and weakly coupled point. But it's even more interesting. So we can achieve, because we can make this this frequency dependence so sharp, and in fact, we can make it sharper than the anharmonicity of our qubit. We can essentially tailor the coupling rates, or the coupling rates of different transitions of the qubit independently. So, the 1-2 transition that we spoke, as we mentioned, for the transmon is different from the 0-1 transition, and we can take advantage of that with this very sharp coupling to tune these independently. And so why is that potentially interesting? Well, basically the transmon makes kind of a boring artificial atom. So it has what's called a ladder structure in quantum optics. And basically the relation between the transition rates are fully set by its nature as being essentially a perturbed harmonic oscillator. So I get that, there's a simple relationship between the transition rates of kind of one set of levels to the lower set of levels. And for the 1-0 to 2-1, it's just a factor of 2. And what this means is I never really have metastable states in this atom. And so it has kind of a boring level structure if I think about quantum optics. Just because I'll mention it a few times, I'll define this ratio beta as the ratio of these 2 relaxation rates. But as I mentioned, because I can make this very sharp dependence, we could imagine that I can design my coupling points such that I have, say, constructive interference of the emission at the 1-0 frequency, while I have destructive interference at the 2-1 transition, right? So I can suppress the coupling of the 2-1 while enhancing the coupling of the 1-0. And here I could make a beta, which is very much less than the standard 2, or I can do the opposite. So I can decouple, or I can strongly couple the 2-1 transition and decouple the 1-0 transition. And I can make beta much greater than this 2. And this is interesting because if I can reach this regime of beta much greater, or in fact, we probably want greater than 10, essentially I can make effectively the 1 level look metastable compared to the 2-1 transition here. So if I can do this, I can effectively now turn my boring ladder system into a much more interesting lambda system. And it's kind of, anyone who works in quantum optics knows there's lots of interesting things you can do with lambda systems. So this was kind of an interesting goal. So it's basically this: if we can make this frequency dependence sharp enough, if we can control the transition rates of these individual levels, and if we can, based on numerical studies, if we can kind of push into this beta greater than 10, we can make it an effective lambda system and really kind of enhance the richness of our system for doing quantum optics. These are what some of our real qubit, our systems look like.
Sorry,
yeah.
I have a question about the previous one.
Sure.
Yeah. So
Sure.
when you have got that effective lambda system, your original system was transmon with anharmonic labels in the theory. Sorry, please go back one more slide if I can ask you. Yeah. So here, like you are showing 0 and 1, and you can have level 2, which is anharmonic to 0-1 transition. So when you are showing the other picture, is it starting from that, like that artificial atom which has anharmonic level like 0-1 and 1-2, which have different transition?
Yeah. So I mean, maybe I guess this could actually be, well, no, that's okay. The idea is that, yeah, so here what I'm plotting is the 1-0 coupling and the 2-1 coupling, which again become like the relaxation rate or the coupling to the bath. And it's, it depends a little bit on the transmon parameters, but if I can, I can pick the transmon parameters and then these parameters so that there's a shift between the 1-0 frequency, a shift between the 1-0 frequency and the 1-2 frequency. So the 1-0 transition, the main point is it's like I arrange it so the 1-0 transition, say, is at a constructive interference frequency, while the 1-2 transition is at a destructive interference frequency. And so I can do that, because they're, it is anharmonic. And then, that's the point, is if I can make this peak sharp compared to that scale, then I can try to arrange to do that, right? So I can have this very, I can make it so, and, real numbers are something like, the 1-0 transition frequency might be 5 gigahertz, and we might have an anharmonicity of like 500 megahertz, so that this would be at, the 1-2 would be at 4.5 gigahertz. So if I can make, the width of this peak kind of a gigahertz or half a gigahertz, then I can achieve this very high ratio. So here are some.
Sorry. So that you will be able to control by putting the number of coupling, or how will you control that thing?
Yes. So the width you change by changing the number of connection points, the number of coupling points. Yeah. So here are pictures of two devices, or micrographs of two real devices. So this is why I talked about 3 and 6. So we have a first device where we had 3 connection points, and then a second device where we have 6 connection points. So this is kind of a large scale. So this is kind of a 5 by 5 millimeter chip. And you can see this is our transmission line coming in, our transmission line going out, or I guess, sorry, transmission line going out on this side. And you can see, so it's coming in, this is where the qubit sits. So it interacts with the qubit. The photon microwaves interact with the qubit, go away, they kind of meander here, this kind of centimeter distance, and then they come back, meander for a centimeter, and then come back again. And it's the same idea over here, just now I have 6 connection points and more meanders in between the connection points. And then zooming in, so this shows our actual qubits. So these are the transmission lines coming in, whoops. These are the transmission lines coming in and interacting with our qubit. And basically what you see here, this is just the capacitive, one of the capacitive plates of our transmon, which get very thin because they're just interacting with a lot of things. So this is one plate of the transmon capacitance, the other plate of the transmon capacitance. And what you can barely see here is the squid, or the Josephson junction. So much smaller than everything else. And similar idea here on the 6 connection point device. Okay. So the first thing that we can do with this system is just do spectroscopy. So, what we do is so this, for people who know about microwaves, this is just a standard vector network analyzer measurement. So we're just putting in, we're measuring the transmission through the transmission line. So we put in a signal, a microwave signal at a particular frequency, so 48 gigahertz. And then we just measure the transmission, which is the color scale here. And what we see is that, at particular points in frequency, we see a big dip, which corresponds to, so it's basically when we're far away from the qubit frequency, all the microwaves just go through, they don't interact with the qubit. But when we hit the qubit resonance frequency, the microwaves actually get reflected strongly. And so there's a big dip in the transmission. And basically how big this dip is tells us how strongly the system is coupled, the microwaves are coupled. And then what we're doing on this axis is now we're changing an external magnetic flux. So we're putting a magnetic flux through the squid, through this tunable Josephson junction, and in that way we tune the frequency of our qubit, right, in situ. And so what you can see, so this is our typical spectroscopy curve, where we're changing the flux, we get a kind of cosine modulation of the qubit frequency. So we trace out the qubit line. But then the other thing that you can see is that there are places where this line is dark. So we have strong coupling, we have almost perfect reflection. And then we have places where the line starts to almost disappear or becomes much weaker. And there we know that we have weaker coupling. And this is just the same plot for the 6 connection point device. So again, we see the tuning and we have strong coupling and weaker coupling.
I have a question.
So sure.
Hi. So for that 6 connection point graph, the line shape looks pretty different than the standard spectroscopy dips. So is there a reason for that? The blue one?
Yeah, so this is very standard in these kind of microwave things. And the generic term is something like a phanoresonance. But it basically, what's happening is that we have some, there's some stray scattering. So, we're putting a signal in, there's some stray reflection. So, and we're getting some stray signal, or another way of saying is that maybe, you have the impedance of your line isn't a real 50 ohms or only real. There might be some reactance or some, so some imaginary part of the impedance kind of gives you the same kind of effect. But those things distort. So these things distort the line shape a bit in a way that's fairly well understood and kind of seen all the time now. But so when we do our fitting, we kind of we correct for these things a little bit. So we get these asymmetric line shapes. But yeah, this is very well known in the superconducting community. So we can take some standard formulas for what this transmission line shape should be, and we can fit those things. So just for each flux, which corresponds to a different frequency of the qubit, we fit that line shape and extract gamma 1. Yeah, we extract the gamma 10, which is the coupling to the line. And then also this little gamma 10, which is the dephasing rate of the qubit, essentially. So the decoherence, which has a term. So this gamma 5 or gamma 10 has a homogeneous broadening part, which is just the coupling to the line or the relaxation divided by 2. And then it has a pure dephasing component, which is what we call this gamma 5. So which in our system would come from background magnetic field noise or background charge noise. So just fluctuations of the qubit frequency, essentially. But anyways, so we can fit this formula, and this is what we get. So here we plot in red, we have the coupling rate for the 6 connection point, and in the green, we have the coupling rate for the 3 connection point, and then we also have the dephasing rate. So we can make, basically we can say we get the qualitative result that we see, that we get this kind of very strong modulation of the coupling rates. We also see that we get, so we can go from very high to very low. And we also see that we get roughly what we expect, which is a factor of 2 between the width of the 3 connection point and 6 connection point device. Now I will make,
Hello,
there's
please?
no theory plot here, or let me just finish my sentence. So there's no theory plot here, and that I'll say because quantitatively in this device, we are off by about a factor of 2 in the prediction of the width. So actually narrower than the predicted width. And so this is, so that's why I didn't put a theory plot, because basically there's no adjustable parameters in the theory plot. You know, the width is just set by the number of connection points that you have. Now in more detailed, we've done more detailed microwave simulations that kind of can reproduce this. And we think it's basically some stray or parasitic microwave effects, which we think we can improve on the next round. But from a practical point of view, what we're really interested in is, in this case, is essentially what's the on-off ratio of the coupling. And for the 6 connection point device, we actually got an on-off ratio, or kind of the maximum coupling to minimum coupling, of almost 400, which I think is kind of a record for on-off, coupling for waveguide QED. So sorry, did I happen to answer your question?
No. So Chris, sorry. So what you have got with this multiple connection is the strong frequency dependent coupling. But what about getting to ultra strong regime like that? Is it possible using these kind of things?
I think so. I mean, we just hadn't done that in this experiment, or we can certainly, here we actually had relatively, these devices, these transmons were relatively weakly coupled. I mean, here everything is normalized, but we had something like, couplings of 10 or 20 megahertz, out of 5 gigahertz. So that's strong coupling, but very much perturbative. And so I think, typical couplings for transmons are easily, without even doing anything fancier, an order of magnitude larger than that, like 150, 200 megahertz, which isn't quite ultra strong coupling, but I think, would be kind of push things into like a deeply Markovian regime, non-Markovian regime, which we didn't achieve here. And I think you could probably go, with flux qubits, you could probably get into the ultra strong coupling regime, but we just hadn't looked at that here.
No. So sorry, Chris, if I am understanding it, you are saying by using multiple connection, you can kind of sum up all the coupling, even though they are, as you said, within dipole approximation, but effective coupling can be like beyond, can be in the like non-perturbative regime. Is it possible that way, or you don't think so?
I believe so. I'm just to be clear, we did not do that in this particular experiment, but yes, I think it should be possible to also be able to do that. Not that I know of.
Okay.
Not that I know of.
Okay.
So, I mentioned that we were interested in extracting the rates of higher levels. We can get the rate for the 0-1 transmission. We just do this simple transmission experiment and fit the line width to get all the rates. As it turns out, that doesn't work for the higher levels. It's quite a bit more involved. Since I've gone much more slowly than I expected, I won't go into the details, but mainly the point is we can extract these rates. So we can use a combination of well-known atomic physics effects. So for instance, we can look at the Outler-Town splitting when we do the two-tone spectroscopy to get the coupling, between the 0 of the 1-2 transition to the line. And then we can also independently measure the 0-1 coupling by looking at the saturation of the transition when we drive hard, so we get a power broadening. And by combining these, we can get out the gamma 2-1 level. So again, just a detail that is somewhat difficult to measure the gamma 2-1, but we could do it. And what we found is that, so for the 3 connection point device, we could get a beta, so this ratio of 2-1 to 1-0 of about 13 or 14, and in the 6 connection point device, we could get 55. So kind of very well into what this regime where we said we could really think of this as a lambda device or as metastable. So, these measurements kind of indicate that we reach this regime of metastability, or we've made an artificial lambda system. And so just as a benchmark of this, so as I mentioned, there's a number of interesting effects in atomic physics associated with lambda systems. So people think about using them for single-photon transistors and all kinds of different things. But a very characteristic effect, and also a characteristically coherent effect in lambda systems is electromagnetically induced transparency, or EIT. And this is where I have essentially, I drive the lambda system, I have a two-tone drive, and I can have quantum interference of how the system moves between the different levels. And this can suppress transitions, or I get a very narrow window where the system doesn't absorb one of the pumps. And that's called this electromagnetically induced transparency. And so as a benchmark to test, we think we've created a lambda system, but also it's important that it should be coherent. We looked at, can we see electromagnetically induced transparency in this system, in our effective lambda system? And basically the answer is yes. So what I'm plotting here is, on the left side, I have two theory plots, and on the right side, I have the corresponding data. And then it's just two different pump powers, which I'll describe. And then the axes here are, I'm measuring, here so I have two tones. I have something that I'll call the pump tone, which in this case is a strong drive between 1 and 2. And then I'm just varying that frequency. And then I have, or actually, sorry, P is the probe. So I have a weak probe between 1 and 2. And then I have a strong control tone, which is driving from 0 to 2. And the idea is, so if I plot these things, when I come close on this axis to the 0-2 transition frequency, I start putting photons into, I drive the system into the 1-2 manifold, and then I can see reflection in the 1-2 manifold, or I see a suppression of the transmission of the 1-2 transition. So we kind of can read it this way. When the control tone starts driving me out of the ground state, I now see scattering from the 1-2 transition, right? And then, one more detail, the 0-2 transition, because this is harmonic oscillator, there's essentially a selection rule that says I can't go from 0 to 2 directly. And so we're actually driving this as a 2-photon transition. So we're driving at 0, 2 divided by 2. And then that's actually even though it's second order, it avoids the selection rule. But what we can see is that, we see what we expect. We drive the system into the 1-2 manifold, we see scattering from that, but then you can see, there's a thin line in the middle where that transition, where that scattering is suppressed. And this is the electromagnetically induced transparency, where what's happening is I now get an interference effect of how the system moves, so that the different paths, so the system can go this way, or the system can go this way, between the paths, and I get a quantum interference that suppresses the scattering. And this is, and this is a hallmark of lambda systems, and it also importantly tells us that the system is coherent. So I can have these interference effects. And this is for experts, there was some controversy in superconducting systems about, there a long time ago, people published a paper saying they'd observed EIT, and people said, no, you haven't, you've observed the Ultrastrong splitting. And then there was some back and forth. And so the point is that we can do fitting, you have different line shapes for EIT and the Ultrastrong splitting, and we can do that fitting, and we find, in this low power regime, which is what we expect, we definitively see EIT, and then if we pump much, much harder, you see a splitting, but the line shape agrees with the Ultrastrong splitting. And really what you get is that those are two regimes which you can calculate analytically, but numerically you can interpolate in between them.
So Chris, one more question about your plot, the transmission plot in the right side. So I see the number is like 7 into 10 to the power minus 6 and something like, let's take 500 or 550 into 10 to the power minus 6 between the lowest transmission versus highest. So is it like if you have, means if you stop this control beam, you will have zero transmission is like 550, or what do you mean by here?
Yeah, so I mean, I think actually, I mean, the best way
Mm.
to put this is I think this is more or less arbitrary units.
Okay.
So I think it's just in this case, we didn't have an easy way. We always have to do when we have like kind of the real calibrated like t=1, or something. We have to be able to do some kind of in situ calibration experiment, which is very difficult, in this cryogenic setting when your experiment is at the bottom of a fridge, right? And so we have various tricks, in certain situations, we've had various tricks to how we can work that out. So like for the basic spectroscopy, what we can do is we can tune our qubit very far away, measure the background transmission, and then we measure with respect to that, right? So that's our bare bones calibration. And we just didn't have a way of doing the bare bones calibration, in this experiment. So yeah, we could think of this as basically arbitrary units. So more you can see that this is really some kind of like volts or something, at the network analyzer. So don't think about it too hard, but you can look at kind of the relative size of the dip.
Okay. So Chris, one more question, that the deep or the peak value will be around omega p, around 1-2 transition, I guess. The peak in the
yeah. So I mean, well, I think it's when it comes close to when. Well, I guess that's what it happens is that when it's I think it's when you can have some detuning of both of the drives from, say, the exact. So if you think I'm driving from 0 to 2, but I can have a little bit of detuning, and then I'm driving from 1 to 2, but I can have a little bit of detuning. And so I think it's when the detuning matches, and so basically I end up driving a now I have a kind of I have a resonant virtual transition, but then that ends up creating the interference. So I think it's when these detunings match is when I get the interference. Or I think another way of thinking about it, like there's some rotating frame where if I have a detuning, my interference is rotating and it averages away. But then when these match in the rotating frame, I have a slow, this becomes slow, and then I can see the interference.
No, because I was wondering your x-axis, is it omega p or the detuning or something? Your x-axis?
No, so in this case, it's the raw omega p. Yeah, so this is it's the control tone, but what you can think about it is, so it's the 0-2 divided by 2. Again, because we're driving, so it's a raw frequency on the, at the network analyzer.
In the middle one, and also in the right one. In the right figures?
Yes, yeah. So the axes are the same.
Okay, the x-axis is omega p, and y-axis is
the x-axis. Yes,
so
yes.
Y is transmission amplitude here. So one of the cut, I guess.
Excuse me?
No,
say it
I'm
again.
saying for the right side, you have y-axis, which is transmission amplitude, and x-axis will be omega p by 2 pi, something like that.
Well, okay, so in all of the plots, so sorry if this is confusing, in all of the plots, the x-axis, sorry, the y-axis is this control tone, so it's kind of close to omega 0-2/2. The x-axis in all of them, so they're all the same, first of all. And then, so the x-axis is the probe tone, so this is close to the 1-2 transition frequency. And then the color scale in all of them is the transmission, and it's kind of arbitrary units.
Yeah, on the right side.
Well, the right side, no. Oh, the green curve. Yes, sorry. So the green curve, yes. So now what this is, so the green curve is like a line cut. Exactly. So I picked some, I think the arrow shows which line I'm cutting, right? But it's basically in the middle of this feature. So now I'm showing transmission versus the probe frequency. And so we see, we see the dip, which is the scattering from the 1-2 transition, but then the recovery now where that becomes suppressed by the quantum interference.
So that's why I was saying that deep probably around omega p around 1-2 transition.
Yes, yeah. So it's near, in this case, it's very much near the 1-2 transition because I'm near the center. Yeah, sorry about that.
Okay.
but in general, so you can see how the suppression or the kind of EIT kind of follows this line, right? And so this is, and because we're doing a 2-photon transition, the slope of this line is 2. But the point is that this is what I was saying, this line follows where the detuning of these two transitions kind of line up with each other.
So Chris, can you get the beta value from this kind of plot or not possible?
Can I get what?
Beta value, like beta larger than
yeah.
You're saying here.
Yeah, well, from this plot, yeah, I think so. I mean, it's been a while since I thought about this fitting, but I mean, it is another thing that we can do. I mean, you can calculate. So when we say, we measure essentially all of the parameters of the system, right? So like I went quickly through some of the measurements, but we can measure all of these coherence rates independently, right? Okay. And you can tell from there, so we say, oh, this thing is in the beta 50 regime or something like that, and then you can actually calculate whether you're in the EIT regime or the ATS regime. Okay. So, I mean, it will tell you, you have some pole that becomes a real or imaginary, at some point, where you kind of split, at least theoretically, between these two regimes. So we could calculate from the parameters that we have, that we measure independently, that we're in the EIT regime. But then, yeah, the point is that we can also get it directly from, now we can measure the scattering, observe it, and we can, fit the EIT line shape versus the ATS line shape, which is basically here, as you can see, the EIT line shape is I have a broad dip, and then subtracted from that, another narrow dip or something like that. But I have two things on top of each other. And for ATS, I have two separated peaks. In both cases, I have two peaks, but in one case, they're on top of each other subtracting. And in the other case, I just have two peaks that are separated. Okay. So I think I went much more slowly through my introduction than I expected. So I think we're at 10 o'clock, and I just covered one of the experiments I was going to cover, but I guess I can stop there since there were also a number of questions. So I guess are there more questions then?
Or we can listen to you little more.
Okay, I can talk a little bit more if people want, sure. Okay, so at least I can kind of go quickly through the next section, which is still kind of,
please.
Yeah, which is okay, so I can do that, which is kind of preliminary work or new work. But yeah, so we're looking at making programmable topological waveguides in synthetic dimensions. And this is work, this is the team that did this work. Team student. So what is a topological waveguide? So here I'll highlight an experiment from Oscar Painter's group, which was in PRX, and they call it exactly quantum electrodynamics and a topological waveguide. And what did they do here? They made, it's kind of interesting, a lumped element waveguide. So they made a waveguide where instead of just being, if you know anything about microwave theory, when people write down kind of how a waveguide works, they often write down a kind of an effective lumped element model of kind of LC oscillators. You describe the waveguide as coupled LC oscillators, right? And then you kind of take the limit of those LC oscillators getting small. So here they made a waveguide explicitly by coupling a bunch of LC oscillators together. So you just have a chain of explicit LC oscillators, so that they're coloring here red and blue. Now, there's a number of interesting things for doing that. Partly they do this because now they can make this very, very high impedance, or they can make the speed of light very slow in these waveguides, which is then interesting for seeing kind of non-Markovian effects and things like that. Or essentially you make the wavelength of the microwave small by making the impedance of the waveguide very high. But in this particular paper, they did something even more interesting, which is that they actually alternate the coupling between the waveguides, or between the resonators. So you have one capacitor plate here in red, another capacitor plate here in blue, and every other one you can kind of see has kind of a big spacing and a small spacing, right? So they have this alternating coupling. And as I'll describe in a little bit more detail, this basically makes a model of what's called the SSH model, which is a kind of prototypical model of topological effects in kind of 1D. And it's one of the first topological models that people wrote down, which actually originally described transport in dimer chains, so in polymers. But the main thing that's interesting, I mean, is that when I do this, whoops, oops, sorry. My thing is crashing. Okay, sorry. So first of all, when I make this alternating coupling, it actually opens up a band gap in the pass band of the waveguide. But more interesting, the topological part is that essentially if I end the chain with closed dimers, I end up being in a topologically trivial regime and I just have a gap. And then if I end the chain with open dimers, I end up in a topologically non-trivial thing, and I end up with 0 state edge modes that exist in this waveguide, which I'll explain a little bit more. But this kind of inspired us to think about, okay, can we make topological waveguides for circuit QED? And I'll do this very quickly. Our platform for this is a tunable cavity, so a tunable parametric cavity. So we have a superconducting transmission line that we terminate with a capacitor on one end. So this creates an open circuit boundary condition that allows us to talk to the cavity weakly. And then on the other end, we terminate it with a squid. So this circuit that I've introduced before, which is a tunable inductor, right? And this creates, if the inductance is very large, this is effectively a short circuit boundary condition. But if the inductance is a bit smaller, I get somewhere in between. So essentially, what I do is I make a cavity with a tunable boundary condition, and I can now tune that by applying a magnetic flux here. And importantly, I can tune this flux through the squid at gigahertz frequencies, or at 20 gigahertz. So at the same frequency as the qubit of the modes, or even higher than the frequency of the modes. And it turns out that this allows me to induce essentially parametric effects in the system. So another thing that we do is we make this cavity very long. So I actually have many resonant modes that I can talk to. So here is a device where we have, say, like 5 or 6 resonant modes, which are just different. I have lambda over 4, 3 lambda over 4, 5 lambda over 4. But I have a number of modes that I can talk to in my measurement bandwidth. And essentially what we can find in the system, this is what it looks like, but I'll skip that. By choosing to pump at certain frequencies, right? So I can induce, I'm sorry I'm going so quickly, but just to mention some of it, we can, by pumping at, we induce a parametric coupling between the system. And essentially what it is the squid has a cosine potential for the system. And so if I expand that cosine to lowest order, and then I also have the pump coupling. So if I expand the cosine to lowest order, I get kind of these operators, the A1, A2, A3 describe my different modes. And when I square this, I get all of these cross terms, right? So I have all these, all of these quadratic interactions between the modes, but all of those have a particular frequency dependence or time dependence in the interaction picture. And so then by picking the frequency of my pump to match the time dependence of particular transitions or particular interactions, I can make those slow in the appropriate rotating frame. So I want to pick out, say, the interaction between 1 and 2. I just pick that difference frequency in this case. Yeah. So in general, I have cases where I can pick the sum of 2 frequencies, and that gives me a Hamiltonian like this, which is parametric down conversion, or I can pick the difference, and that gives me a beam splitter coupling where I can move photons between. Or in a language more of kind of quantum simulation, this looks like a potential pairing potential and a hopping term. And importantly, I can control the amplitude and phase of these terms by controlling the amplitude and phase of my palm. And so this allows us to make in the system programmable lattices, right? So the idea being, I can think of doing I can make a photonic lattice in this device, but each of the nodes of my lattice are now actually frequency modes of my cavity. And so that's what I mean that we work in so-called synthetic dimensions. But the interesting thing is that I can create the graph here, the graph of connections, in a fully tunable in situ way. So I'm just turning on pumps at room temperature, turning on and off pumps at room temperature, and I can change from having a triangular lattice, a square lattice, or I can have a 1D lattice. We've studied this in a number of different cases. So we actually just published a paper this week in PRL where we did a quantum simulation of the bosonic Kreutz ladder. I'm just advertising it here, but we get interesting, lots of interesting things that go on, and we can explain it very well.
So Chris,
I'll just skip this, yeah.
Yeah. So this coupling is between different frequency. So
yes, so it's different frequency modes, right? But it creates, yes.
So it's not.
And so this is what we.
So it's in the frequency space coupling. It's not in the coupling between different, let's take qubits or different.
Yes, correct. Yeah, so it's exactly. So this is what we call this, in the quantum simulation world, this is called synthetic dimensions. But yes, exactly. So here, I mean, I think you could use the same thing where I could have actually discrete resonators, and then I could couple them, I could have some coupling and I could parametrically couple them in this way. So I could turn the coupling on and off. But here we're making a kind of hardware efficient version of it, where we're actually just we have just one cavity and we have multiple resonant modes of that one cavity. And then we're making couplings between those resonant modes. And essentially the graph of the coupling tells us about, defines the kind of what lattice we're simulating in this synthetic dimensions.
Then will you call it different from this Painter paper which you just told a little early? Because so theirs is real. They have a kind of real space element to it, right? But here we're kind of thinking, but then it's not programmable, right? They make one device and they get one, they get one thing. Mm-hmm. Here we have a system where we can simulate multiple different systems in the same device, right? We can simulate different. Why I'm wondering, because this SSH model which you mentioned, that give these zero modes or the topological modes in real space, which will be at the boundary. So how would we see that?
Well, we still have a boundary here, essentially, because the way I think about it is the dimensionality of my model is essentially defined by the number of nearest neighbors that each mode has, right? So in 1D, that in general, that means that I should have 2 nearest neighbors for each node. And so I can still define an edge as being, I'll have some special nodes that only have 1 nearest neighbor. And so those are my ends. Those are the edges of my system. And then the other ones are the bulk 1D modes have 2 nearest neighbors, right? So if I go back to,
so Chris,
and I can have, in a 2D system, I would have, 4 nearest neighbors or something like that.
So, but Chris, will you say then you are seeing zero modes or topology edge modes in frequency space? Because that's what I'm confused. Okay. So
yes, so we're seeing edge. I mean, the zero comes in, and the zero part of it comes as a frequency thing. I mean, so you have, or it's in the gap.
So that's why I'm confused, because that's called energy frequency. That's why zero modes. But here you are having frequencies are coupled. So how would I even say?
Well, the zero, zero is kind of, the point is that I define a zero, zero is the center of my band gap, right? Okay. So like in that Painter thing, the zero mode was still at I can see in the old slide at 6.7 gigahertz, right? Because that's the center of my gap. And then it's just the idea is that from solid state, I tend to define zero energy as the center of my gap, and then I have positive and negative energies, right? But the zero part is just the center of my gap, right? Or it's the the rotating frame frequency I'm going to work with.
So
and then the edge part of it is the edge is a spatial component, but yeah, now my spatial component is in synthetic dimensions.
And you will
But
also say
the edge, yeah.
Your zero modes are in the gap, somewhere gap or something, because it has to be protected by gap.
Yeah. So the zero mode is, so the zero part ends up being, zero is the center of my gap. Okay. The zero energy is the center of my gap, essentially, in this language. And then edge will be, I think there is a real topology or a real, graph structure to our connections, and then we can define an edge as being the ones that only have one nearest neighbor compared to the bulk that have two nearest neighbors.
And so, Chris, how many of them you can couple? Means how long your 1D chain will be?
So far we've gotten to 6, okay. But we're making new device. We're cooling down a new device where we hope to get to more, or maybe we've gotten to we've gotten to 6 or 7. Okay. I think these guys had like 9. And I already said some of this work, but yes. So the point, the SSH model, I get a gap. When I end with closed dimers, it's trivial and I just have a gap. And when I end with open dimers, I get a non-trivial topological phase, and I end up with these kind of protected zero modes that live in the gap. But as you can see, right, the zero mode is, at 6.6 gigahertz or 7 gigahertz in this experiment, but it's zero in the sense that it's the center of the gap.
And Chris, what are you y-axis just in that plot? X and y-axis
in this plot?
Yeah, y-axis is, what is that? S21.
So here they're again measuring transmission in this plot thing there. So S21 is transmission, okay. And a log unit transmission through their transmission line as a function of the
in their case, but in your case, what do you mean by that?
Yeah, so okay, so what I can say, like what we can measure, I mean, what can we say? What are we do spectroscopy experiments, and what's the idea? So we have some mode, right? And we can we have a mode, and we can just measure around that mode. And so now I see our typical reflection dip in this case, right? And I see one dip at one mode. But now I can turn on my lattice, right? So I turn on some graph of connection between, in this case, 4 modes. And what I see is the mode around this, the plot around this one frequency now splits, right, into 4 modes. So I see that I have coupled modes now. And if I looked around the frequencies of each of the individual modes, I see a similar thing. I see now coupled modes at each of these frequencies. And how do I measure transport? So yeah, now my my modes are at different frequencies, right? So to measure transport, I have to measure essentially frequency conversion. So I can probe around an individual mode and I see some dips, right? But now what I can do is say I can put in a signal at omega B with my lattice on, and then I look at what comes out at omega A. So I get transmission from B to A, which is actually kind of a frequency conversion transmission. So now I see some transmission.
Which you call transmission.
Yeah, so it's frequency conversion, which is transport in our synthetic lattice. Right? And so we can do that we can explore that for all of the nodes. And I won't go into too much, into the detail here, but being able to look at this transport also allows us to kind of map out the wave function of our states, right? Because we can see that, and we show this in this Kreutzlatter paper, some states will transport to some modes, but not to other ones. And that kind of tells us that the state that we've created maybe has support on one set of nodes, but not the other ones. So now, because just to go very quickly, so here's some of our experiments. So we're measuring, here what I'm plotting is we're measuring a full scattering matrix of here, it's a 5-site SSH model, where I kind of have one weak bond on the end over here, and then a strong bond on this end. And what I'm plotting here is, this is essentially the full frequency dependent scattering matrix. So the diagonal is looking at this reflection from the individual nodes, which I can think of as essentially measuring the spectrum of the system, right? So it's measuring the frequencies of given sites. And then the off diagonals are these are the transport. So this frequency dependent transport between nodes. So this is transport from from this A to the next site, to the next site, to the next site, and so on, right? And what you can see here, and this is what is predicted, what's interesting is when I have this one kind of dangling bond on the end, you see that I get, I have a kind of isolated state that's in the center, but then it doesn't couple very strongly to any of the other sites, right? So in this sense, so here, we don't have, well, I have a smaller system, but you can see that essentially I have some gap, and then I have this state living in the center of it, which kind of, and then it's fairly isolated to this side. So it doesn't couple to even sites at all, as it shouldn't. And we see a little bit of it here because the decay length isn't that far, but it doesn't really make it to the other side. And interestingly, we can do things. So now if I make one of the advantages, where I call this tunable, so now I can adjust all of this in situ. So here I was showing these numbers here are basically the coupling strength. So I have 2.5 megahertz coupling, 10 megahertz, 2.5 megahertz, 10 megahertz. This is set by changing a pump strength, right? So what I can do is in situ, I can just tune all of these to be now 5 megahertz. So now I have just a standard type binding model, right? And because this has an odd number of sites, I have a zero mode, but we can see now that this zero mode is completely delocalized, right? So I don't have the kind of the topological features of the SSH. I have a zero mode, but it's delocalized and it's not protected.
So what do you mean by delocalized? Sorry, Chris, I did not understand.
Well, you can see the mode exists, all across the lattice, right? So I have this kind of zero mode in the center, and I see it kind of spread out over the whole lattice, basically equally. And I can see I also get transport from, say, here, to the center and things like that. So I have the zero mode isn't localized to one end of my synthetic lattice, right? Which is what I saw here. Or we can go, and what I can do is I can, for instance, I can rearrange things. So now I have my dangling bond on the other end, and now you see that zero mode moves to the other end instead of, move from the left side to the right side. But I can do all of that in situ. So I can essentially kind of move my
Chris,
zero mode around.
Sorry, Chris, I would have expected no zero modes in the case when you have this kind of coupling, at least in SSH model, because that will be the trivial insulator kind of things. Right.
So I'm playing a little bit of a trick, which is that if I have an odd number of sites in the SSH model, right? So I have an odd number of sites, which mean, so if I have an odd number of sites and I essentially have one dangling bond on the end, I get a localized mode at that end. And then here we have, what I could also do is I could make, here I kind of break the alternating pattern. So I make a kind of defect in my SSH model. And you see, then I get a zero mode pin to the defect in the center. Or here I go to 6 states. Now I have a number of even states. And here I'm just showing, this is the topologically non-trivial. So this is the topological phase where I end and open dimers. And you can see in this case, I have zero modes localized on the two ends, right? And what you can see, I mean, it's not perfect, but you can see things kind of decay. These should be two separate zero modes, and you can kind of see that the transport decays going in this direction, and kind of the same here. This one couples to this one some, but then it decays and very weakly couples. So I really kind of see this kind of decay, that these are kind of two separate edge states that kind of don't talk to each other that much. So again, this is kind of preliminary stuff, but I think it's very interesting, because again, I think we could make a waveguide that's fully programmable, and we can move these topological states around and turn them on and off and things. Okay. And now I'll definitely stop there because I'm very far over time.
Okay.
Okay, but any last questions?
Yeah, I have a question. If someone else is not asking, I will ask you.
Okay.
Saptarshi, do you want anyone else to ask first or?
No, please go ahead.
Okay.
Please go
So
ahead.
Chris, so I missed one part. You said that if you have like this one, which I see in the picture now,
Mhm,
here you have zero modes at the two end.
mhm,
But if
mhm.
you have opposite coupling like 10, 2.5, 10, 2.5, and 10, you would not expect anything, right?
Yeah.
So,
Correct. And I think we just didn't have the pretty plot for that one. But I think in general, that's what we see. Or I think we were having, maybe in this case, we're having trouble getting it with in this device with the 6-mode system. But in general, we can see this. We've done this with more like 4 modes, and you kind of definitely see that. But so yeah, but I think we're still working on this. But I think exactly you see these qualitative features. Yeah.
and Chris, means in the case of tide, means because it's probably small, so you do not expect really band gap and all this to appear because there is nothing like band also in this very small number of. Uh,
Yeah. Yeah, I mean, I think so. I mean, so you're very much correct. I think if so part of it is like, it's like if I look at this system, am I seeing are these modes starting to form a band? It's not so well defined. So in some sense, you can make this comment that which is not incorrect, that bands are defined really in the thermodynamic limit or large system limit, and topology of the system is defined, it's the topology of the bands. And so therefore it's defined in this large system limit. But I think what, people are starting to see very much experimentally, so I think, their system, like in the painter system, was a bit bigger than ours. But like if we go back to the picture, it's maybe they had 12. I guess we could count the modes, right?
yeah.
But you can see, like, so they have 12 in this experiment, I think. And you can see, okay, 12 isn't a thermodynamic system, but you can start to, you can believe that this is a band, right? And then there's a band gap here, right? So, and you can see the emergence of these 0 modes. So, again, it's like, okay, is it topological or it's not? That's a bit tenuous. But and formally probably not. But I think what's being realized is that in already relatively small systems, excuse me, you can start to see these features coming out. So I don't think I think at least experimentally, we don't really need to fully be in the
No, I understand.
thermodynamic limit to understand things. And I think what's interesting is you can, and there's a trade-off, which is that, here, I think we do understand these systems. Like you see, like in these plots, everything's not perfect, but red is data and blue is theory curve, right? So we have some simple, very simple scattering theory of coupled modes, and we can explain the data in real detail, but in some sense the topological, the intuition from the kind of thermodynamic topological model explains the qualitative behavior, right? So I can, I can calculate and do these nice fits, but that doesn't tell me why I have a 0 mode here and not here, right? So I can still, the thermodynamic model, limit model, kind of gives me the intuition of what's going on. And I'm not getting into it, I didn't show it, and we haven't, but we can certainly see qualitatively, it's like let's say the localization length of the edge mode, depends on the ratio of these couplings. And like, we can see things like that, right? So we can see, which is kind of, this is the extreme. When these couplings are the same, then the modes aren't localized at all, and things like that. So, a lot of the, both qualitative and quantitative predictions of the topological model come out even already at this small scale.
And Chris, what are the advantages of doing in the synthetic dimension, in your opinion? Is it like also protected by dissipation or kind of those things which will be more in real space, or is there any?
I mean, I think that, I mean, one thing honestly is just like the programmability, you know, and then the simplicity and essentially like the hardware efficiency, right? So, I showed these, I won't go into it. Well, I showed this plot of our quartz ladder experiment, and that was done literally in the same device as this SSH experiment, right? So we can do these two different, very, fairly different, these simulations with fairly different graphs or topography in the same device. And I can't do that if I make a real space lattice, right? Now, I can still have some programmability, and definitely using these parametric effects, give me this great, this big programmability, so I can tune these couplings. So in the Oscar Painter thing, they actually have just a physical capacitive coupling, so they can't tune those devices, right? So they get what they get. And here we can tune them, and which I think is interesting because I can do things like move an edge state from one side to the other, right, by changing these couplings, which I think is interesting. But I think the same parametric effects could be used in a real space lattice also, and you would gain. So I wouldn't have the full programmability because I have a fixed real space lattice, but I would gain the advantage of I can still have the programmability in the coupling. So I think it's very promising. And we are working on experiments. Yeah, if we want to do things like mix, so we for other types, here, one disadvantage of this system is everything's bosonic. Although we can load, we can use other things to load single photons in. But for other experiments, we might want to mix. We might want to do simulations where we have some like matter fields or qubits, and then bosonic fields, which are like gauge fields or something like that, right? And then we might be easier to have a real space lattice where I have qubits and oscillators and things like that, but still use parametric coupling that makes things tunable.
So Chris,
there is one question from Rupak. Maybe he can unmute himself and ask if it is okay. Hello.
Well, okay. I can see. So they ask, can just state again the case of the impurity at the center and the existence of the zero mode. So this is what I'm showing here is that again, it's a small system, but the idea is that so for the SSH, I should have alternating like 10 2.5 10 2.5, right? And so I've kind of broken that. So what this looks like is I have it's like I have two, and if this were bigger, you would see it more clearly, but it's basically I have two domains of my SSH model, right? So I have, say like an odd domain and an even domain, and then they're coming together, right? So this looks like this point where I kind of break the pattern is like a domain wall in my one-dimensional lattice, right, in between the two domains. And then again, the theory predicts that when I have this domain wall, I should get a zero mode that ends up being pinned, or localized at this domain wall. And so that's, we think we're seeing here.
Okay, is there any further question?
I have a question. Regarding your slides on Waterloo splitting and EIT in the giant transmon, so you had showed it in lambda type of system. So I was curious to know, like in the atomic system, like the atomic vapor or the cold atomic systems, we can see quantum interference effect. Like EIT and Waterloo splitting, also in V type of system as well as ladder type of system. So I was wondering whether such you can see these effects in the giant transmon in ladder type or the V type of system as well.
I mean, I think it might depend on different things, and I think. I think from what I understand, it's kind of easiest to observe the EIT when I have like a metastable level. And certainly there can be different ways that I have a metastable system. And certainly it's true that really the ordering of the I think the levels isn't so important. So it doesn't have to be that the metastable system is in between the other two. But I think, yeah, it helps to have, from what I understand, it helps to have a metastable system. And so if I can arrange that in the ladder system, you know, I can do that. And I think it's just harder. I mean, I think that's part of it. So what I call the original transmon a ladder system, just basically because all the rates are kind of similar, which is part of it. And they do tend to just transition, you know, because it's like a harmonic oscillator, they transition all in a row. So if I can relax various of those conditions, yeah, I think I can see, you know, EIT or various quantum interference effects. But it's, you know, so maybe lambda isn't the most important point, but the point is here that I could make a metastable level in my qubit.
So Chris, I have one more question, sorry. To extend this question of Rupak, that if we have like this system, like this SSH, you are talking mostly single photon behavior, but what about going beyond like single photon and looking at interacting regime? Like one of the goal was wQED to have strong photon-photon interaction.
Right. Yeah, no, I think that, I mean, I think this is a very, I mean, so if I, like I said, okay, so for the kind of, yeah, I mean, yes, I mean, or at least generalization. So I think if I wanted to do, if I wanted to look at, you know, photon-photon interaction basically looks like anharmonicity of my lattice, right? So the energy of 2 photons is slightly different than the energy of 1 photon, right? So essentially I can make a lattice, you know, if instead of making a lattice of harmonic oscillators, which is what I showed you was, if I make a lattice of n-harmonic oscillators, you know, I now have, you know, I have something with photon-photon interactions, right? Now, I think in our system, it probably would be easier to do. I think we can do that. We'll probably be able to do that with a real space lattice. Because essentially, you know, what we have is the transmon is just an n-harmonic oscillator where I have really strong photon-photon interaction, right? I have this massive n-harmonicity. But I can tune continuously there, essentially by kind of trading off the capacitance and the Josephson inductance. So with more or less the same circuit, just with some tuning of the fab parameters, I can have a harmonic oscillator, I can have a qubit, or I can have an anharmonic oscillator, which is then, you know, a system, something with on-site photon interactions, right? So please, so I can mix all of these things together.
No, Chris, my point was in the topological sector, if we try to break the interaction, is it possible, you think, within your, the kind of one, because that will be more interesting about the, that how zero modes behave in the presence of interaction.
Yeah, so I think, like I said, I think probably it would be easier to do the interactions. I don't even need to flip here. If I had, well, not or just I could use kind of the same scheme, but yeah, probably if I made, well, yeah, or we could think of, it would be, you know, here they have really harmonic oscillators. There's not even Josephson junctions. But if I took this one and now I replace, you know, this linear inductor by a Josephson junction, but I could, you know, if I make the Josephson junction relatively big, it won't become a qubit. It will just become an anharmonic oscillator, you know, but essentially it's that anharmonicity between the 0, 1 and 1, 2 level tells me what the size of my interaction is, right? So, you know, I have so very much, I think we can do kind of models with on-site interactions. And my only comment is probably to do that, we would want to go back to some kind of real space lattice, you know, probably still I would still do tunable parametric couplings, but it'd be a real space, but with a real space lattice. But then we can really do that. And you can do with these oscillators, you can make both positive and negative anharmonicity. So you can kind of do repulsive and attractive interactions. And I think it's, yeah, it's a very interesting, you know, it's a very, very rich system.
Okay, if there is no more further questions, we thank Chris Wilson for this wonderful talk and all the discussions. Thank you very much. So we
Okay.
can
Thanks, Chris.
we can end the meeting now. Thanks a lot again,
Yeah, yeah,
Chris, for this
Yeah.
beautiful
Yeah.
lecture.
Thank you very much for having me.
yeah. Thank you.
Okay. Bye.
Bye.